Okay. All right, I think it started.
All right, cool.
All right, thank you so much. Thank you so much. And hello, everyone. Thanks for joining. Thanks for coming. My name is Valentin. I work for GridGain Systems as a product manager. Um, at GridGain Systems, we work with distributed databases. As a matter of fact, we created one, and that's our product that we sell and we provide services for. And our platform is actually based on the Apache Ignite project. I don't know if you've heard of it or not, but it's basically a distributed database um, that is focused on like in memory processing and providing performance and scalability to the applications. And of course, it's an Apache open source project. So if you're interested in the topic, feel free to join the community. You're always welcome. So today, what I want to do is I want to share a little bit of my experience around distributed databases, and specifically about internals of those distributed databases. And essentially, what I will do is I will build a very kind of simplistic, very trivial distributed database, although it will be quite fully functional in terms of what we are going to require from that database. And I'll build it from scratch in Java. So I will go through some theoretical stuff. I will show all the components that we're going to have, like essentially create an architecture step by step, adding more and more components along the way, and adding more functionality along the way. And I will also do that in code as well. So we'll have a little bit of slides, a little bit of live coding, and so I think it's going to be fun. And it's quite a big presentation. The amount of information is quite a lot. So feel free to stop me if something is unclear. And also after each kind of section, I will also give you an opportunity to ask questions. So don't wait until the end of the talk, because again, it's quite a bit of information. So I definitely would like to make sure that everyone understand everything along the way. So with that, let's get started. Yeah, so first of all, the raffle that we have, these are the books that we're going to that are included in the raffle. So we'll have 3 winners at the end, and you will be able to choose one of those 3 books. The first one, the Designing Data Intensive Applications, is more kind of a generic. It's a very cool book, actually. I would definitely recommend to read it. I have it right next to me all the time, basically on my table, on my desk. It's very useful and very informative. Database internals is more kind of more a deep dive into the database technologies, like how the data structures are organized and these kind of things, or more kind of a low level book. The second one is the one that I quite honestly haven't read, so I cannot tell too much about it. But as far as I know, it's really it's a great book as well, and quite informative as well. So that's the link. There is the link in the chat as well, so you can just click it there, or you can use the one on the slide, and I will also get back to this at the end of the presentation as well. All right, so let's start building our database. So as I said, distributed databases nowadays are quite popular. They're used for many different use cases, and they're actually quite complex. Providing multiple different APIs, multiple different options in terms of how you can store the data and how you can process the data, and what you can do with it in general. Here again, I want to just demonstrate some basics in terms of how those databases are built. And the reason why I'm doing this is when you work with a database, with a distributed database, it's actually quite important to understand those basics, because it really helps to uh, get the most from such systems, from such databases. I've seen a lot of people who would treat kind of distributed database as a black box, hoping that it will kind of magically provide scalability and provide performance. And then when it doesn't happen, they kind of blame the technology. which might be, reasonable to a certain extent, but but pretty often it's actually very valuable for you to know how they work under the hood, at least, on a basic level, because that helps to properly, create your data model suitable for this kind of database, because it's really different from, traditional relational databases and these kind of things. So it might be really important. But of course, again, the database that we're going to build today is very simplistic. It will provide only very basic functionality. And as a matter of fact, these are the requirements that that I have for the database that I'm going to create. So let me go through the requirements first, so that we all understand what we're going to create. First of all, the only in-memory data storage will be supported. So, I don't want to worry too much about persistent storages, like kind of disk-based storages, because it makes it much more complex. And also, in-memory databases are quite popular nowadays as well. Even like pure in-memory databases without, disk-based storage whatsoever. And it's one of the use cases for Apache Ignite, for example, which we see quite a lot. So I'm not only doing this for simplicity, it's actually a real design that you might see for many distributed databases, just pure in-memory storage. The second requirement is key value API. What it means is that we will have kind of, hash map-like API with just two methods, put and get, that's all. And they will work with string data types, meaning that both keys and values are just strings. Again, just not to worry, about complex serialization, deserialization, and this kind of thing. So we'll just stick with very simple data types. Any mature system, of course, will provide you support for different data types and for, storing custom objects and whatnot, but we'll just simplify this on that level as well. And then, of course, we're building a distributed system. So we want this distributed system to provide scalability. This is actually why we're building it in the first place. The whole purpose of a distributed system is to provide scalability. And what I mean by scalability here is basically just an ability to run multiple computers or multiple servers that are essentially just combined into a single system, right? So from application perspective, application can treat multiple computers as a single database. That's pretty much what scalability means. And scalability actually has kind of two aspects into it, which essentially create those other two requirements, 4 and 5, that I have here. The first aspect of scalability is what I call computational scalability, meaning that we want different computers in our system to process different requests, right? So let's say your application creates thousands requests per second, right? And you have two computers in your database. So essentially you want 500 of those requests to go one to the first node and other 500 to go to the second node, essentially kind of load balancing between those two. And if the load increases, if the load grows on the application level, we want to just add computers into the system so that the system automatically picks it up and starts rebalancing requests across those nodes as well. And the second aspect is data scalability, which just means that we want to be able to store more data, having more computers in the system. So let's say a single computer provides you with 100 gigabytes of RAM, right? We're in memory storage, so we're limited by RAM. So if a single computer provides you 100 gigabytes of RAM, then to store 200 gigabytes of data, you actually need two computers. If you want to store 300 gigabytes of data, you need three computers, and so on and so forth. And again, if the data set grows and the amount of data we want to store in our database grows, we want to just add computers into the system increasing the overall capacity this way. And of course, both of those things, they must happen automatically. So the system must do this automatically, reroute those requests when topology changes, when we add more nodes, and the data has to be redistributed. Application only should invoke those public API methods, the put method and the get method, and that's all. Everything else should be taken care of by the system. And throughout this presentation, we'll essentially build a system that will do exactly that. We will have public methods on the API, and I will show you how the system can achieve those automatic request routing and automatic data distribution automatically within the system itself. Any questions on that before we go forward? Because again, like understanding the requirements, of course, is important. So I want to make sure we're on the same page in that regard. All right, if there are no questions, let's go. So as I said, I will create the kind of architecture diagram, adding more and more pieces along the road. And after kind of each step, after each section, I will also do that in code as well. So let's start with building our server-side node. So essentially, to enable our database on the server side, we need to have a server-side process running on that computer that we want to use for our database. So this blue box essentially represents this process. And the first component that we need there is the storage itself. In our case, it's going to be pretty straightforward because, again, we have in-memory storage. We store data only in memory. It's just key value API, and therefore we can just use, essentially concurrent hash map in Java as an underlying structure. Of course, if we add more requirements, if it becomes more complex, this underlying structure will also change. But for our requirements, it's enough to have just a concurrent hash map. The storage only stores data, and it is able to serve those requests, meaning that if you want to put something there, it will know how to put this data in this underlying structure, and also it knows how to give it back. But since we want to request the data and update the data across the network from a client application, we of course need some kind of a communication layer. And for that, we will add a separate communication component into the system, which will essentially be responsible for, of course, all the networking, like creating server sockets and these kind of things, and accepting connections and establishing those connections, maintaining connections, and all this stuff. And it will also implement some sort of serialization protocol, which will allow it to communicate with the client application. And the client, which is shown in green, will be essentially embeddable into the application. So it will be kind of an API instance which will be embeddable into your application. And of course, it must have the same communication component as well in order to be able to communicate with the server node. So they will implement the same protocol with certain set of messages, for updating and reading the data. And on the client side, we will also have the public API, which will have those two methods that we're looking for. And the public API is what will be used by the application. So this will create like a very basic, in-memory database with those two public methods. It's not distributed yet, but that's where we start before we go into scalability. So let's see how it looks in code. So I have a little project here. It is on GitHub, so I will send out the link after we finish here. It's all there with all the code that I will create, during the presentation as well. So you can check it out. You can play with it. You can modify it if you want, and these kind of things. So let me go through the project a little bit first of all, just to explain what we have here. Because some of the things are pre-coded and some of the things are will be are commented out, and I will bring them bring them in when needed along the road. So let's start building those components that that we need for the database. So again, we need a server node first, the server process that needs storage and communication. So let's basically start there. So this is the storage class. The storage class will implement the storage component. It has two methods, very self-explanatory, put and get. And those methods are just responsible for this kind of internal representation of the data and for operations with that representation. So we will create our underlying data structure which will be, again, simple map where the key is a string and the value is also the string, because that's the data types we're working with. And we'll call it data. And this will be just a simple concurrent hash map. Oops, concurrent hash map. And in put and get methods, we will simply redirect to those, needs to be data.put. And get method is implemented the same way. We read the data from this map. I will also add some outputs here so that we see what's going on server nodes, and we'll use it when we do some testing. So I'll just do like put, and I will print out the key for the operation. And the same, I'll do the same for the get method as well. So we'll have get here. So that's our initial implementation of the storage. That's all we need. We have this concurrent hash map as our underlying data structure that stores the data, and we also have methods which can be used by other components to update and read the data. This is not the public API, by the way. This is just the kind of internal API of the storage component that can be used by other components. Specifically by communication, of course, because that's one will invoke those operations based on the requests that are coming in. So the communication component is it's pre-coded because it has a little bit of boilerplate. I didn't want to do it live. It's also it's however pretty straightforward, pretty obvious. It has a server socket. It has a start method. I'm using like a very kind of vanilla Java API here. It's a synchronous communication, kind of a thread per request model, which will not be used, of course, in a mature database. But again, I do a lot of things for just simplicity here. So it creates a server socket here with port 4000 by default, or just it can also use like 4001, 4002. This is just to be able to run multiple nodes on the laptop. I'll use it for testing and we'll see how it works. So this is just a start method, and it essentially just creates a server socket and binds to a certain port. And then the listen method is the one that accepts the connections and creates kind of a processing threads for those connections. And the communication protocol is implemented through this request interface. So essentially what happens is that whenever we accept a connection, we then accept requests in the form of implementations of this request interface. And the request interface looks like this. It's very simple. It has only one method handle, which accepts the storage. And that essentially kind of creates this link between the storage and the communication within the system. And whenever communication receives such a request, an instance of a request interface, it then invokes the handle method providing the storage that was actually provided here as an argument for the listen method, and just writes back whatever the handle method returned. And there is also one more method here. It's method execute, which does it kind of farther way around. It sends a request to a certain address provided here. So again, it connects to this address and then just writes the request into the stream and gets the result back. So essentially, this listen method is the server side, which waits for requests and processes them, and execute will be used on the client side to send those requests when we want to execute a certain operation. So let's kind of build something from those components. So we have a storage, we have communication, and we also have this request interface, which we'll be utilizing. So starting with the server side. So within the server, as we discussed before, as it was shown on the diagram, we need to have a storage component. Oops. And we need, and I can initialize it right here, which was be like this. Okay. And we also need the communication as well. All right. And I also have this start method here, which is responsible for kind of initializing everything. So storage doesn't have any lifecycle, at least for now, but the communication needs to be started. So we need to invoke the start method, which again will create the server socket and bind to a certain port number. And then we also invoke the listen method, which starts accepting connections and processing requests. And here we provide the storage that we also have just created. So that's essentially creates again this link between communication and the storage component. And the main method will just create an instance of a server and invoke the start method. So let's take a look at the client now. So the client also has a start method, which actually for now will be empty because there is nothing to initialize. And it also has put and get methods, which are public API methods. So these are the methods that will be invoked by the application that will have kind of a reference to an instance of this client. So within the client, we also need the communication instance, because we need to be able to connect to the server node and send requests. So we don't need to initialize the communication because it's not, client is not accepting connections. It's not listening to requests or anything. It only sends them. So in a way, it's implemented. We don't need to initialize it. So the start method will remain empty for now, although we will use it going forward. We need to implement put and get methods, however. For that, we will use the method execute that I've mentioned before. And here we need to provide an instance of a request and also the address, right? So for the former, we essentially need two implementations of this request interface for the put operation and for the get operation. So let's create those. So I will call the first one will be put request. So it needs to implement request. Since put operation doesn't return anything, it can be just void here. So we will be returning null from the actual implementation. So for the put request, we need to send the key and both the key and the value, like along with the request. So I will add those as fields to this class. And I will initialize them through constructor here. And in the implementation within the handle method, I will call storage.put using the key and value that I have here. And the same needs to be done for the GET request. Also implements request interface, of course. In this case, however, it needs to be based on the string class because we want to return a string value, which is the value that we fetch from the database. So, and we only send the key now. So for put request, we need both key and value because that's what we need to execute an update. For the GET request, we only send the key along with the request, but we do return the value that we read from the database. So we return storage.get with the key that we provided here. All right, so going back to the client. So now for the put operation, we will use the put request. So we create just an instance of the put request here, providing key and value. And now the address. So the address, right now, we actually don't have any mechanism for the system to internally kind of figure out where to send a request. So what I will do for now is I will just hard code the loopback address with the port 4000, which is the default port number for our communication component. And the same, I will do the same for the get method. So I will also use the execute method. The only difference is that I will be using the get request instance here, providing the key. And again, I will hard code the address in the same way. All right. So that's actually what we've discussed and what was shown on the diagram. So we have a server process with the storage and with the communication and the whole initialization process implemented. So we can actually run it, and let's see what happens. While it is compiling, we can actually go to the client, and we also need like simple tests, right, on the client side, basically kind of to emulate the application that will be using this client component here. So in the main method, what I will do, okay, so it's once the server started, and it says that it started in port 4000, which is what we expect. So let's see what we can do on the client side. So this main method is basically kind of, again, it emulates the application that you can build using the functionality that we have right now. So here within the application, we will create a new client instance. And we will start it. So currently, start method again doesn't do anything because it's empty, but going forward, it will do some work for us. So we need to invoke this method here. And after that, we can invoke put and get methods to update and read the data. So let's have like a simple loop with, let's say, 10 operations. And I will first, I will do several updates. So let's say I will just use string value of with this integer, with the I, and the value will also be something based on the index, so like this. So that will just write 10 key value pairs into our database. And after that, let's do another loop where we will read the data and print something out. So again, we do like iteration of 10, and here we will do like we'll have a string value equals client get. And I'm using the same keys, of course, so that I read the data that I've just written into the database, and then I will print it out here. Let me actually separate the key like this, and I will just print out the mapping. Something like this. So essentially, I just update. I write 10 entries based on these keys, and then I read the exact same keys and I print out the mappings just to verify that everything works correctly. So we have server node up and running. So let's run our client application now. We will, of course, expect that it will connect to our database, to the server node, and execute all those operations. And yeah, we get all the correct results. And if we go to the server node, we actually can see that the server node processed those requests, 10 puts and 10 gets. So let's go back to the slides. So with this, on this stage, we essentially, again, we have our in-memory data storage. And we have kind of a server process that encapsulates that storage. We have the client component that can be used within the applications. Client provides the public API with put and get methods. And we, of course, have the communication layer between those two. At this point, it's not a distributed database yet, of course. It's just a single node database. And so as a next step, we will move on to the fun part, and we will actually create the distributed database. Before I go there, do you guys have any questions that I can answer? If is anything unclear or anything?
I have one quick question.
Mm-hmm.
Hello. Okay. Is there any connection, I'm curious, between what you're about to show us with Ignite or I don't know.
Yeah, that's a good question. Yeah. So it's both yes and no. So of course, like most of my experience lies around Ignite and GridGain platform, which is also based on Ignite. So I have certain bias here, but the main concepts and the main ideas are pretty much the same in any distributed database. Since I'm only touching basics here, they're not going to be very different if you look at different databases. So yeah, I kind of go from kind of using the Apache Ignite as a reference for myself. But again, fundamental ideas and concepts that I'm showing here, they're pretty universal for different databases.
Okay, thanks.
All right. Okay, so let's see how we can add scalability. So as I mentioned before, scalability essentially implies that we want to have multiple computers running as a single database, a single system. So naturally, what we'll just do is we'll start our server process on multiple computers. So let's just add a second one into the picture. So it's exact same process with all the same components, with the same storage and with the same communication layer. However, just doing that is not enough, obviously, because they're not aware of each other. They don't know that they are part of the same cluster. And also the client doesn't know about them. So yeah, it technically can connect to those different addresses, but it doesn't have any information about where those nodes are located, how many nodes we have in the cluster, nothing like that. So to solve that, we need to add another component, which is usually called discovery. This is basically, this is a component that is responsible for what I've just described. It's basically kind of a meta storage that stores all the kind of this um, you know, how to say, this meta information, the system information about the cluster, like how many nodes we have, where those nodes are located, meaning that, coordinates of those nodes, like IP addresses and port numbers for those communication layers that are running on those nodes, and maybe some attributes, or some other information that might be specific to the particular database. But kind of IP address and the port number is the minimal information that has to be there. It's and it, it basically has to happen kind of in a consistent fashion. So all the nodes must have the exact same information and get updates on any changes that are happening in the cluster, also in a consistent manner, like, so that they all have the same information. Um, there are many ways of doing this. It's a, it's as you can think, it's quite a complicated task in general, and different databases approach this differently. And mature databases, they typically will have some internal protocol for that. Like Apache Ignite, for example, kind of creates a ring-based topology, where heartbeats go across the rings and across the ring, and everything is ordered within that ring. Another way of doing this, kind of a more simpler way, which I'm going to use here, is to have an external storage for this, right? So we can use any kind of small database, which can be just a single node database or high available database, that will store all the kind of this configuration and this meta information, for the discovery purposes. If in the Java world, you probably know about Apache Zookeeper, which is one of the most obvious options in that regard. So it's often used for this kind of purposes. Like Apache Kafka, for example, used Zookeeper exactly for that for a while. Now switches to kind of internal native protocol, but it was relying on Zookeeper for that for quite a long time. I will be using a database which is called etcd, which again, for all the practical purposes that we have here, is exactly the same. It's just a very simple key value database that can consistently store this information, and it can also you can also subscribe to updates for any changes that are happening there. It's a database which is used by Kubernetes, for example, for kind of as an underlying storage for all the configurations and anything that we create there, and by other systems as well. So I'll be using that again for a simplicity purpose. So what will happen again is that anytime a new node is started and joins the cluster, this discovery component will read the information from etcd about the nodes that are already in the cluster, and will also write the information, kind of the IP address and the port number of its own, right? So its own IP address and its own port number, so that it's registered in the database, in the etcd database. And also the existing nodes that are currently running, they will get an update about this new node. So this way, essentially, everyone will have the consistent information about how many nodes we have and where those nodes are located. So that's on the server side, right? So this way we kind of achieve that server nodes kind of know about each other, and they essentially form a cluster now. But we also need to do something with the client side, because client still doesn't know anything about this. And we'll do actually exactly the same. We'll just add the exact same discovery component there on the client side, which will connect to exact same etcd database, and we'll get information from there. The only difference is that, of course, it will not have to write anything. It will use etcd in kind of a read-only mode without registering itself there. So let's add this into the code before doing anything more complex. So close this stuff. So discovery is here. It's actually pre-coded as well, because as you can see, it's quite a bit of code. It doesn't make sense to do this live. But let me go through like major major parts of the code here and major steps that we go through. So first of all, we have this topology map here, which is basically the representation of the current topology. And again, we will have this discovery component on every single node in the cluster, and every single node will independently maintain this topology map locally. But the way we design it makes sure that this information is consistent across the nodes, right? So that's the map where we actually store the information. UUID is the key, which is kind of just an ID of the node. The only requirement is that it's unique across all the nodes within the cluster. And integer is actually the port number where this node is deployed, where this node, the port number of the communication component for that particular node. I don't have IP address here because I kind of assume that everything is running locally on my laptop. But of course, you know, in the real system, you will also have an IP address here, and you can run nodes on different servers, different physical servers. So the join method implements the whole logic that I've described of joining the cluster. So it has 3 steps, right? First of all, we get the current information about the current nodes that are already in topology. Like, let's say we have 2 nodes and we are adding a third one. So this third node will run the join method, will execute the join method, and it will first get the information about current nodes. So it will essentially get a list of 2 nodes here, the ones that are currently running. It will then create a etcd watch. This is the etc functionality for getting those updates. Essentially, what's happening here is that this lambda will be executed and invoked anytime there is an update in the database. So that the update happens, we get a notification. So this way, those 2 nodes that are in topology, while our new node joins, will get the notification. So they will get a notification through this watch mechanism. So the lambda updates the map and then just prints out the new topology. And finally, we register the information into the etcd. So we write our own local ID and our own port number into the etcd database, so that again, existing nodes get notifications here through the watch. So that's how discovery works. Again, on a very basic level. There are many cases that are not really supported here, like living nodes and some other corner cases, but this is enough for our purposes. This is enough to form a cluster and to make sure that you have multiple nodes that actually act as a single whole system, as a single system. So let's see how we use this discovery. So on the server node, of course, we want to have this discovery component right here. So we'll create an instance. And what I haven't mentioned before is that this communication start method actually returns the port number right here, right? So the one that it has chosen to create the server socket for, it will return it from here. So we can actually use that in order to pass it on to the discovery. So we have the port number, and therefore we can invoke discovery join. I'll create the ID in a second, and here we pass the port number, and the ID is basically just again, this ID just has to be unique for every node, so I can just randomly generate it using the UUID random UUID method. So that, again, that makes sure that we join the cluster, and this discovery join method, again, will just go through the whole process of joining the topology. And if all nodes do that, they will be aware of each other and they will know where all the nodes are located and all that. So now let's see, now let's add the same to the client node. We will also have the instance of discovery component right here. Will be discovery. So I also need to invoke the join method here to get the information from etcd, to connect to etcd and get the information about the cluster, about the nodes that we have in the cluster. However, we don't need to provide anything for the client node because the client node again doesn't register itself within the discovery process. So I will just use nulls here for the ID and for the port number. All right. So let's see what we get from that. Let's start a couple of server nodes. So we'll start 2 now because we have a distributed system now. So we should be able to start 2 nodes and they should be able to discover each other and to form a cluster. So let's see if that works. So that's the first node, and etcd, by the way, is up and running on my laptop already. So the first node starts on the port 4000, and it shows the topology, which has 1 node, which is correct, which is expected. Let's start 1 more. So this one now binds to port 4001 because 4000 is already used. And the topology that it prints out actually has 2 nodes, which is exactly what we want to see. And if we look at the first node, same here. So it also printed out the new topology because this new node just joined. So we have 2 nodes running. We have 2 independent processes running here, but they both are aware of the fact that they are actually part of the same cluster, and they have all the consistent information with IDs and the addresses of those nodes. So with that, let's run the client. I'm not changing the logic of the application itself. It stays the same, but now it again connects to the cluster, and it should also print out the topology, indicating that we were able to connect to the cluster, and client also has all this information about the nodes, how many nodes we have, and where they are located. However, and again, of course, we still have all the same correct results. We were able to write the data and read the data back. However, if we go to the server number 1, we'll see that it still processes all the requests, all the 10 updates and all the 10 reads. And if we look at the second node, it actually is idle. It doesn't do anything. Which is, of course, an issue. Again, the reason why we want to have multiple nodes is that we want those multiple nodes to process different requests and to distribute the data. And of course, the reason for that is that we have the address hard-coded. So both put and get operations on the client use the port 4000, which is hard-coded here, which will change as the next step. So let's go back. So again, we've added scalability, right? Meaning that we kind of have we satisfy the basic requirement that we can run multiple computers and they will know about each other and they will form a cluster. But we're not really using it in any way right now. And we'll start with the automatic request routing, and we'll get rid of that hard coding of the IP address and the port number that we currently have within the client public API methods. Any questions before I go forward? All right. Awesome. So, so again, like we have discovery both on server side and on the client side, and as you can see, actually, we don't really use it. You know, like all other components, they're not connected to discovery yet, and we're not really using this information that discovery provides. So naturally, you know, it seems that we can use the information. However, at this point, it's not that obvious, right? Like, okay, the application invoked an update operation, for example, a put method that we have right on the public API. What should the system do, right? All the discovery provides is just a list of addresses, right? It doesn't really tell us where to send certain requests. And what we want to achieve is we want to have like a mechanism that will consistently send certain keys to different nodes, right? So I want, let's say I have two nodes and I want key 0 to be sent to the first node and key 1 to be sent to the second node, for example. So how we do that? For that, we will add one more component to the client for now just the client. And we'll call this component mapper. And this mapper component does exactly what I've just described. It provides the mapping between a key that we're invoking a public API operation for, and the node where this key is stored and is supposed to be processed. So essentially, the node which kind of owns this key. So what mapper will do, so the application will call the API. API will, before going to the communication layer, it will actually request the node information from the mapper, providing the key. The mapper will then go to discovery, you know, get the topology, which is again just a list of nodes. Do some magic here, do some magic there, and return the information about that node into the API, and then the API can, you know, send the put request or a get request to a particular node because it now knows the address of that node. So the question is, what is the magic, right? If you work with, you know, hash map structures and anything similar, you probably already thought about hashing, and that's exactly what we're going to use here, and exactly what, you know, most key value database use for these kind of purposes. And we'll start with a very basic hashing. All we'll do is we'll just get the hash code of the key, and then apply the modulo function based on the number of nodes that we have, which that will give us kind of an index of a node in the list. And then we will use that index to choose the node from that list, right? So if you have 3 nodes, the function will essentially return kind of 0, 1, 1, or 2, and that is just an index in the list. So let's implement that and see how we can use that. All right. So I already have the mapper kind of stub here. It doesn't really have any implementation yet. So I have this, so ignore the commented part for now. We'll use that later. For now, I will only have one method, this method node, which gets the key and returns the information about the node. This discovery node is, by the way, is internal class within discovery, and it has the ID and the address. So it's kind of just a descriptor of the node. So, so how do we do that? So first of all, we need the discovery here, right? Because the mapper relies on discovery to get the information about topology, to get the list of nodes. So therefore, we need to have a reference to the discovery component of our current node. So we have discovery. No, I don't want a new one. No. I don't want to create a new one here. I want to actually initiate a Druid constructor because I want, of course, to use the one that maintains the information that I already created within the server. So the node method will first go to discovery and get the list of nodes. I have the get topology method here for this. which gives me the list of nodes that are currently running within the cluster. After that, I will calculate the index of the node. So I'm using ABS function just to eliminate, negative values of the hash code. I'm using, standard Java hash code for the string, and then modulo topology size. So I get an index in this topology list based on the size of this topology. And then I just get the item based on that index. All right. That's pretty much it. That actually implements the hashing. So now we have a mechanism that will consistently give me a certain node for a certain key. Of course, assuming that topology doesn't change, right? So if we have like 3 nodes and we have a topology of 3 nodes, regardless of how many times we call this function, and regardless of which client instance we call this function, it will always give us the same result. Again, assuming topology doesn't change, we will talk about this later. But for now, let's assume it does not change. So having this mapper, we can go back to the client and add it as one of our components here within the client. Again, it will be just an instance of mapper class. And we want to inject discovery here because mapper relies on discovery to get the information. And once we do that, we can get rid of this hard coding. So now instead of hard coding an address or assuming basically where the server node is, we can just use mapper for this. So mapper will we'll call the node method, provide the key, and get the address. And the same happens for the get method. So now instead of hard coding the address or inventing some configuration where we will provide the configuration or the list of addresses or something like that, we basically just rely on discovery and on this hash-based mapping algorithm to define where certain key is stored and where a request for a certain key should be processed. So let's run the application. So I already have server nodes up and running, and the code did not change, so I don't really have to even restart them, but I will restart the client. All right. So the client, again, everything works as it worked before. So it connects to discovery. It shows us that we have 2 nodes. It shows us all the correct results. The difference, however, will be on the server side. So we will scroll down all the way here. So this is our previous run. So that's the last run. So we have only 5 put operations and only 5 get operations. And we have like 1, 3, 5, 7, 9. And if we look at the second server node, it now does some work finally. It's not idle anymore. And it actually processed the request for other 5 keys, right? So this way we achieved this kind of load balancing between different nodes within our database, so that some keys are processed on one node and other keys, different keys, are processed on the second node. All right. Let's move on to the next step. So again, of course, we achieved this automatic request routing this way. So again, the requirement was that application will only invoke put and get methods, and the system will do everything else automatically for it. And that's exactly what happens. Application uses put and get methods, and then internal discovery mechanism and internal hash-based mapping determine where a particular key is stored, and the system automatically distributes the loads across the nodes that we have, and sends different requests, routes different requests automatically to different nodes. And actually, if you think about this, if we go back to this result, in terms of data distribution, we also achieved certain results, right? Because the data is actually distributed across the nodes now as well, simply because we have these 5 operations, these 5 update operations, for example, have been executed here on the second node, which means that these 5 keys are actually stored on the second node as well, and other 5 are stored here, right? So essentially, we already, by achieving this request routing specifically for put requests, we actually achieved the data distribution itself. However, here's an issue. Before, I told that we assume that topology doesn't change, but of course, in a real system, it will change. you will want to add more nodes into the system, and also it sometimes even happen accidentally, like nodes leave the cluster and whatnot. But let's see what happens if we add a third server node into the topology. So of course, it binds to the port 4002, which is the next available. And discovery works perfectly. It shows us that we have 3 nodes, and all 3 nodes know about all 3 nodes, which is exactly what discovery is responsible for. So that's all good. However, if I run the client again, and I actually will run it without updates. So I will not update the data. I will only read the data. We already have all the key value pairs in the database, right? So we can just have an application that only reads the data, and it will read those exact 10 keys. And let's see what happens in this case. And of course, we should not expect nothing good, because again, topology changed, and therefore the mapping changed, which basically means that some of the requests were processed on this new node, like 2, 5, and 8, for example, right? So those GET requests were sent to the third node, because based on the new topology that changed, the mapping also was updated, right? So the hashing, our hash-based algorithm now gives us the third server for some of those keys, 2, 5, and 8 in particular. And for that reason, we have some of the values that are read from the database. They're actually not read. We get nulls instead of the actual value, which is of course an issue. By adding a new node into the system, we essentially completely have broken consistency of the database, which is of course unacceptable. So basically, by automatic data distribution here, I not only mean that we want to kind of be able to store different parts of the data on different nodes, which we already can do by just running put requests on a certain stable topology. But I also want to make sure that data is redistributed automatically as well when topology changes, when I add a node into the topology, for example. So essentially, I want those 3 keys, 2, 5, and 8, to be moved to this new node so that my request routing mechanism is consistent with the way the data is distributed within the cluster. So let's see how we can do that. This is actually usually called data rebalancing, which is exactly what I've just described. It's a mechanism of redistributing the data, reshuffling the data across the nodes so that it is always consistent with the request routing that mapper provides. So how we achieve that? First of all, we want to be able to notify the storage when something changes, right? So whenever discovery detects that there is a new node, for example, we want to notify the storage because the storage has the data, and the storage will be the one responsible for picking the parts of data that needs to be, sent somewhere else. And therefore, Discovery needs to be able to notify the storage. This is a trivial step because Discovery already has, the actual notification mechanism provided by etcd database in our case, and therefore it will just redirect it to the storage. After that, once the storage gets a notification about a topology change, what it will do is it will go through all the data that it has, essentially through all the keys. And for every key, it can check with the mapper, and we'll use the exact same mapper with the exact same hashing function, because we want this routing mapping to be consistent with the data distribution. Therefore, we're using the exact same algorithm. So it will check with the mapper where a certain key is stored, where a certain key belongs. And if it belongs locally, it will just, stay there. And if not, it will send it to the node where it actually belongs based on the new topology that we have after the change, right? So topology changes, Discovery detects the topology change, notifies the storage, and then the storage checks with the mapper, which now uses this new topology because it was updated by Discovery. And mapper tells for every key where this key should be stored. And if it's not stored where it should be, it is sent through the communication layer to the node where it has to be. So this, red arrow just represents the whole redistribution process on the communication level. The only issue with that, like I've mentioned, that storage will, go through all the keys, right? Which obviously is not efficient. This definitely, smells like an issue, because we don't want to go through all the keys, because number of keys is, generally speaking, unpredictable. All right, we can have 0 keys, we can have a million keys, we can have a billion keys. And we don't want this rebalancing process to depend on number of keys that we have. And we just simply don't want this linear complexity. So how can we optimize that? And to make sure that, this, at least the step of verifying which data belongs to the local node and which data does not, doesn't take that much time and doesn't depend on the number of keys that we have. To optimize that and to fix that, we'll use a technique called data partitioning. And idea is pretty simple, actually. All we do here is we split our key value pairs, split our keys essentially into groups, into chunks. And the requirement is that the number of those groups, or as we call them, partitions, is constant, right? So let's say we have 10 partitions in the database. We just say that, upfront in configuration, or maybe it's a characteristic of a database itself. And regardless of how many nodes we have, regardless of how many keys we have, we always have 10 partitions, right? So this number never changes. So we have 2 nodes, for example, and then every node will have 5 partitions. We add more nodes, then partitions are redistributed. So now we actually distribute partitions rather than keys. And therefore, the rebalancing process has to only check the this limited constant number of partitions rather than all the keys in the database. And the way we actually achieve that in terms of kind of what the algorithm should be. We use the same kind of hashing approaches. However, we'll have this, naturally we get this kind of two-step process, right, to get from key to the node. So first we map the key to partition, and then we map partition to the node, right? And for the first step, we'll use the exact same function, hash function that we've used before. We'll get the hash code. We'll use the math.abs for, to eliminate negative values. And when we'll apply the modulo function, but now we will use partition count rather than number of nodes. And again, partition count never changes. It's a constant number. It does not depend on anything, not on number of nodes, not on number of keys, nothing. So this mapping, hash code, never changes for a certain key. Partition count is also constant, and therefore, this first step in this mapping also is also always consistent, right? So for any key, it will always give you the same result, again, regardless of number of nodes that we have. So this means that if a key goes to partition number 5, it always will go to partition number 5, regardless of anything. And it doesn't even depend on whether you actually have this key physically stored in the database. It's kind of a logical mapping. So which means that all that changes is the second step, the mapping between partition and the node, because that one will change based on number of nodes that we have. And all that means is that we currently can do rebalancing based on partitions. So we rebalance partitions rather than keys. And therefore, within this check process, verification process that we have on the storage level, we only have to check like 10 partitions, for example, or any other constant number of partitions that we have in the database, rather than checking all the keys that we have, which basically provides us with the constant algorithmic complexity as opposed to linear complexity that depends on number of keys in the database. All right, let's let's see. Let's take a look at the code. So let me first kill everything here. And now let's implement the rebalancing. And first of all, I will start with the partitioning, right? So at this point, we have this kind of flat data structure with the, where we have a single concurrent hash map which stores all the key value pairs. We want to partition this data. And to partition this data, all I will do is I will basically create kind of a two-level map data structure where the top level map will have an integer as a key. Oops. And this integer is, of course, the partition number. And the value will be another map of actual key value pairs, but now for that particular partition. So this way we just split the data between multiple partitions, between different partitions within our storage underlying data structure. So now we have to, of course, update the put and get implementations, because we now need to get the data first the sub map based on the partition number, and then update that internal map. For that, we actually need to go to the mapper first, and I will uncomment this part here, which we now need. So as I said, the mapper now works in a kind of two-step process. It first maps key to a partition and then partition to a node. So we have, I will have two separate nodes for that. The first one maps partition to a key, which will basically just do this. So we'll get the hash code, we'll apply the ABS function again to, get rid of negative values. And then I will have a partitions constant, which I will just hard code. And again, to emphasize that it never changes. So for example, I will have 10 partitions, right? So that ensures that this mapping, again, it never changes. This is a constant number. Hash code by definition never changes for a key. So regardless of, again, how many times you invoke this for a certain key and where you invoke it, on which server node, or which client node, always gives you the same result. Now, the second part will work similar to what we had before in our method that gave us node by the key. So we'll get topology. I will actually just copy paste this code and modify it a little bit, so that it's clear that it's basically the same. So all we change here is, instead of using the key hash code, which we don't have it here anymore, we'll just use the partition number. That's all that changes. And we can also modify this method because now it can go through this two-step process. So it will first calculate partition based on the key, and then it will calculate, figure out the node based on the partition number. And this final method, partition mapping, is just a kind of a utility method that I'm using for rebalancing. It gives us kind of a full mapping for all the partitions. So this is an array where every element essentially represents a node mapped to the partition represented by the index of this array, right? So if we want to know where partition 1 is stored, we'll just pick a node by index 1 from this array. And I will use this here for rebalancing. But first, let's finish the put and get methods. So now we have a mapper that knows how to calculate partition based on the key, and that's what we need here. So we'll add the mapper here. We already have the mapper created within the server, so I will pass it here through constructor, using constructor like this. So now I will first get the submap for a partition, and I will, in order to do that, I will get a partition number from the mapper. So essentially what happens here is that we will first invoke the mapper, and specifically the partition method that will give us the partition number for this key. We'll get a submap based on this partition number, which will give us an actual data map for this particular partition, and only that we will update this internal map. And same happens here for the get method. All right. So that implements partitioning, but it does not implement rebalancing yet. Rebalancing is yet to be implemented. And it's actually implemented here in this remap method, which is currently commented out. So let me restore it. All right. So this method, again, it basically just implements the logic that I've described before. It gets the full mapping from the mapper. Then it goes through every partition that we have. And for every partition, it checks, it gets the node where this partition is stored from this full mapping. And then it essentially just checks whether this node is the local node, right? In which case, it would mean that this partition belongs to the local node, and therefore we don't have to move it. And moreover, we might want to create a new empty map, if it's not there yet. But if it does not belong to the local node, if the local ID is not the same as the ID of the node where it actually belongs, we remove it from our, top level data map and send it through the communication layer to the address of that, using the address of that node this partition belongs to. So there are several missing pieces here so let's add them. First of all, the local ID, which is the UUID, which represents the local ID of the node. And I will also add it to the constructor in a second. The same happens with the communication. We do need communication to be able to send those rebalance updates and essentially to send out partitions that don't belong locally to other nodes. So we need to wire it up through constructor. I add both local ID and communication like this. All right. And final part is the rebalance request. So we use communication to send the data for a certain partition to the node where this partition needs to be stored. And therefore, we need to implement another request implementation for this particular purpose. So I'll create a new class, which is called rebalance request. So I need to send the partition number and partition data as fields like this. So I will edit here, and I also need to implement request. We don't have a return value, so I can just use void here, and I have to implement the method. And here within the handle method, I actually need to somehow tell the storage no that I have a new partition data that needs to be stored. I don't really have such method yet, so I will let's call it on partition received for clarity, and I will provide partition and partition data here. So all is left is to create the method on the storage instance. And the method itself is very straightforward. All we need to do here is to simply put the data into the database. So I'll update my top level map, which has all the partitions with this partition data that has just arrived. All right. So that implements the whole logic, right? So again, like whenever we need to, whenever we invoke this remap method, we'll go through all the partitions. And for those partitions that have to be moved to other nodes, we'll send them through our communication layer using this new rebalancing request that we've just created. And whenever rebalance request is received by other node, this on partition received method will be invoked and the data will be saved within the destination node. So the only thing that is left is to actually initiate the rebalancing when topology changes. So this remap method is not used yet, right? And as I've mentioned before, we want to do that based on discovery notifications. So discovery has this watch mechanism right here, which essentially is invoked every time topology changes. So we want to invoke something here to notify storage about the fact that topology changed, So what we'll do is we'll add kind of an abstract listener here, which will be just a simple runnable. And the runnable will be provided through the join method. So whenever we join the cluster, we can provide this kind of optional listener to discovery, which will be invoked right here every time topology is updated. For example, when we have new node joining the cluster. And finally, we need to go to the server class and fix everything here. So within the join method, so here we'll provide the link to the storage remap method. So that essentially just means that whenever topology is updated, this storage remap method will be invoked and the whole rebalancing process will be initiated. And finally, the last part is we need to add all those components to the storage that it now requires. So for that, first of all, we need a mapper, which we don't have yet. On the server side, we only created it on the client side. So create a mapper. We'll have a discovery here, and I'll move the storage to the bottom because I need to make sure that all other stuff is available. So what do we need here? We need the mapper. We need the local ID, which is our ID. And we need the communication. All right. So that kind of wires it up and creates all the links between all those different components that we have within the server. And also, let's check the client, see if anything is needed here. Yeah, so discovery join. Of course, we don't need a listener on the client, so we just provide the null right here. And as a matter of fact, we need to check if it's null or not here so that we don't get a null pointer exception. So we invoke the listener only if the listener is not null. For some reason, after a while on Zoom, it gets very slow. All right. I think that's all we need to implement both partitioning and rebalancing. So let's verify that we've actually achieved what we wanted to achieve. And I will basically just rerun the exact same test that I've had before. So I will start two nodes first. Then I will start the client with both updates and reads. I will then add the third node into the cluster and will run the client in read-only mode. And now, since I've implemented rebalancing, I expect that the data will be redistributed across the cluster. And therefore, I will get all the correct results. And my new node will also process the requests for the data that is actually stored there after the rebalancing. Oops, hold on. Yeah. So I have two nodes for now. Now, let me actually, hold on. Just to make sure. Okay, everything is good. Right, we have two nodes. I will restore these lines that update the data in the client, and I will run the client. As I said, it will update the data, and it will also read the data with those two nodes that we currently have. All right, we got all the correct results. Sorry. Let's see what we have on the server node, on the server side logs. So again, it all works as expected. 5 of the keys that we've written into the database and read from the database are processed here on the server 1, and other 5 keys on the server number 2. So now let's kill the client, add one more node to the topology. Right, so it binds to 4002, and we have 3 nodes. So good, so far so good. I remove the lines that update the data so that client only reads the data. And we got all the correct results, which was not the case previously before the rebalancing was implemented. And if we go to this third server, we actually see that some of the keys were processed here, in particular keys 0, 4, and 7. They have been processed on this new server number 3, and we still got the correct results for those keys, which means that rebalancing process work correctly, as we expect. Any questions on this part before I move on to
There's
the
some
last
questions
one?
in the chat.
Oh, okay. Hold on. That's a good point. I didn't look at it. Let's see.
We'll probably get to it, but the questions about how you protect clients during the middle of this from getting bad data. Do you block? Do you do something to allow concurrent reads?
Yeah.
Right.
Yeah, that's actually a great question. And obviously, there are many scenarios which are not covered by this implementation. And I'm doing quite a bit of certain number of assumptions about what I will do with the database. Of course, yes, in the real system, you need to synchronize it somehow. Mature databases that will never block your your applications throughout the rebalancing, because rebalancing can take quite a bit of time. If you have gigabytes, terabytes, petabytes of data, moving it all around obviously might take significant amount of time, and you don't want to be blocked for the whole duration of rebalancing. What will typically happen is that the system will kind of maintain multiple copies of the data, both on the stable topology and during the rebalancing itself. And therefore, when the data is moved from one node to another, you can still read it from somewhere else. Of course, that all makes the whole mapping process and rebalancing process much more complicated in terms of implementation, and that's why I kind of ignore those scenarios in this particular implementation. But yeah, this is a great question. Of course, this needs to be considered, and if you actually implement a real database, you need to make sure that that consistency is preserved at all times. Which will not be the case in this particular implementation. If I run a request somewhere in the middle of rebalancing, I will still get an incorrect result. But again, it's not achieved by locking the whole thing. It is achieved by some more complex concurrent mechanisms where you can still read and update the data even during the rebalancing, and it still stays consistent. Regardless of the rebalancing process that happens in the background.
Along those same lines, you're going to use redundancy, I think, too, right? To put partitions, make sure there's no partition that's only on one node, right? To deal with the outage of a node so that you can not lose data, right? And then you have to synchronize multiple writes then, right?
Absolutely, yeah. So like one of the biggest things probably that this thing doesn't cover, and I'm actually thinking about having a second part of it, covering some other things. But obviously, one of the biggest thing that this implementation doesn't cover is case of nodes leaving topology, right? So I'm kind of talk about what will happen if I add a new topology to the cluster, but I don't really cover what happens if I remove a node from a cluster, or especially if it leaves the cluster abruptly, right? And that's one of the things. And most of the distributed databases will, of course, have kind of a backup, replicas or backups, as we call them in Ignite. Essentially, for every partition, you will have 2 or more copies on different nodes, and therefore, if one node goes away for whatever reason, you still have all the data available. And this also helps during rebalancing, as I said, because when you move the data, you still can read it from somewhere else. So yeah.
So how is that like and not like RAID partition, like on a disk array? Like if you're using RAID, what is it? RAID 1, is it? Or not the mirroring, but the the replication.
I actually, I don't think I can answer that. I just frankly don't know. I would assume that
it sounds like a similar problem being solved at the database, or at the level.
I would assume that they do something similar.
Because you could drop a disk and not lose data, right? Because it moves, copies, and
I'm sure they do something along those lines. It probably is a little bit more complicated because it's a file system rather than just a key value storage. Key value storage. One of the characteristics of a key value storage is that it's extremely scalable. It's very easy to scale because like every key value pair is independent, and you just create this hashing mechanism based on key, and you are done essentially.
If you think about it, a file system is very much like that, right? There's like inodes, and then it's content, right?
Yeah, but it's kind of a hierarchy structure, so it's a little bit more complicated. It's still possible. I'm not. Sure. It's not impossible, but it's just more complicated than just simple key value pair.
Yeah.
All right, let me see if there are any. There was remap rebalancing going on. Yeah, that's basically. So the question is, what happens to the client while remap rebalancing is going on? Does it wait? So yeah, my implementation doesn't wait. And as I've described, it generally will just allow to happen this in background rather than do a full locking. That's the best to select keys. What is the best way to select keys for your data? How it might affect the storage if we change keys for our data? So changing keys generally means that you kind of, again, in a key value storage, there is usually no concept of changing a key. Changing a key just essentially means removing a value from a database and writing it back or something like that. And that's pretty much it. It might end up on a different node. It might end up on the same node, but it's kind of unpredictable. Again, in real databases, you have other mechanisms that allow you to group entries together. Like, for example, in Ignite, we call it affinity collocation. So what happens is that you can configure it in a way, or you can create your keys rather in a way that you can have multiple keys stored in the same partition, within the same partition, and therefore on the same node, and you can have guarantee from the system that will happen. So you can utilize that. But if you just replace a key with a different key altogether, that is considered just a different key value pair, and essentially this is just a removing and writing it back. All right. I guess. All right. I think that's all the questions that are in the chat. So let's move on. There is one more topic that I wanted to cover. And this is, so there's one more issue that we actually have with the data distribution. So we currently, we achieved data rebalancing. So it actually looks pretty good, and functionally it works. Assuming, putting aside those issues that we've just discussed. But in terms of our requirements, it kind of works, right? So we add a new node into the cluster, into the topology, rebalancing happens, and we can read the data from this new node, and we can get correct results. However, let's see what happens in more detail. And I will just go through a sample, data set, some sample data distribution to show a couple of things that we still want to fix. So let's say we have a very simple, we have a financial kind of a application, and one of the data sets is basically just a table or a list of accounts. Every account has a credit card number, which we'll use as our primary key, and then we have, first name, last name, current balance, and whatnot. So let's see what happens if we try to distribute this those keys across multiple nodes. And I will start with a 3-node cluster. So let's say we have a 3-node cluster, and we use our basic hashing function that we've used before to distribute those keys across those nodes. So what will happen is that for every credit card number, we'll calculate the hash code and again apply the modulo function, and we'll use 3 because we have 3 nodes. And we'll get something like that, right? So for every credit card number, we'll get an index of a node where this information about this credit card should be stored. And it will be the number from 0 to 2, inclusively. So 0, 1, or 2. And just to visualize it, that's how it will look like, right? So we'll have 3 nodes. Node with an index 0 will have 3 of those entries. Node with the index 1 also will have 3 of those, and 3 of other entries, and node with the index 2 will have the other 3 entries. So again, so far so good. Now let's see what happens if we add one more node into the cluster. So the data set is the same. The hashing function is also the same, but the number of nodes changes. Therefore, this modulo operation is now applied with the 4 rather than with the 3. So this parameter changes. And the result is this. So now we have, of course, a couple of entries end up on this new node, which has the index 3. And, other nodes are also distributed across those 3 nodes that we've had before. So let's take a look at the picture again. Again, we get some kind of distribution. Some entries end up on the first node, some entries end up on the second node, and so on. So let's compare those two distributions, and let's see what actually changes when we move from one to another. So this is our new distribution, and this is our old distribution. So first of all, we see that there are 2 entries that have been moved from, in this case, node 1 and node 2, to this new node that we have just added into the cluster, and that's good. That's what we want from this rebalancing process. That's what we expect. And that's actually why we add more nodes into topology. We want some data to be moved there so that we can utilize the resources of that new server, that new computer that we've added to the cluster. However, if you look carefully, we'll see that there are also some other movements within the cluster that are not really needed, right? These are just the movements between the nodes that we had before the topology change. And if you think about it, this is kind of a redundant data movement. It doesn't really add any value, because those 2 values that have been moved to the new node, they absolutely add value, because, as I said, because of that data movement, we can utilize the resources of that new server. Moving the data between the 3 nodes that we've had before the topology change doesn't really provide us anything. And on top of that, it actually makes things much worse, because network is quite expensive, and moving the data, reshuffling the data is expensive. It consumes resources, it consumes time. Even with this, simple example with like 9 keys, we have more red arrows than we have green arrows, which is kind of a red flag. And generally speaking, this data movement and this data reshuffling can have very significant, negative consequences. In the best case, it will just rebalancing will just take a lot of time, and you will have significant performance degradation during the rebalancing. So as I said, rebalancing typically happens in the background and doesn't really lock the application workload, but of course it interferes with it in terms of resource consumption, network, CPU, and whatnot. So if there is too much data movement within the rebalancing, it will consume too much resources and will interfere with the application workload too much, and also will take too much time. But that's the best case. In the worst case, it will just saturate everything, saturate the network, saturate the CPU, and the cluster will fall apart, and you will have a downtime and all other things that you want to avoid. So that's a big issue. That's actually a big issue, and there are several ways to fix it. The way we do this in Ignite, and the way I will cover here, is the algorithm that is called rendezvous hashing. So we're still kind of using hashing approach. So nothing really changes on the fundamental level and on the architectural level, but we will change the actual hashing algorithm that we're currently using. So let me go through the algorithm first, like what rendezvous hashing algorithm does and why it helps in this particular case. So let's just pick one of the keys as an example. It doesn't matter which one, just one of the keys that we have in the data set. And what we'll do is we'll also assign a unique ID to every node, which is, that's what we actually already have. I've been using UUIDs for that, but it can be anything like a string ID or whatnot. Just the only requirement is that it's unique for every node. And we will define a hash function, which is calculated not just based on the key, which we had before, but based on a combination of the key and a node ID. And then, we'll also use the ABS function to get rid of negative values, of course. And we'll then calculate this function for every node ID that we have in the cluster and for the key that we want to calculate the mapping for. And we'll get something like this. So we'll get, for a single key, we'll get 3 hash values for all the different nodes that we have, like H1, H2, and H3, for example, in case of 3 nodes, right? What we'll do next is we'll choose the maximum value among those 3. In this particular case, this is the H2. We will call it H max. And the maximum value will just basically point us to the node where this key will be stored. So since H2 is the maximum value among those 3 that we have, we will store this key on the node number 2. All right, so that's the mapping, that's the actual mapping. Sorry, that's the hashing function, that's the hashing algorithm that we use. It's fairly simple. Just instead of calculating a hash for just the key, we calculate hash function for a combination of the key and the node ID for every node ID that we have in the cluster, and then we choose the maximum value out of those out of the list. All right, so now what happens if we add the fourth node into the cluster? So let's say we have node 4, we add it to the cluster. Now we need to recalculate the mapping. So H1, H2, H3, they do not change, of course, because the hashing function is consistent. For the same key, for the same node IDs, it will give the same results. But we'll get a new value for the node 4, which we'll call H4. And now we actually have 2 outcomes. The first outcome is that the H4 is less than H max, the current H max, which is currently H2. In which case, we'll just, H max remains the same. It's still H2, and therefore the key still stays on node 2. And the second outcome is that H4 is actually larger than H max, and in which case it becomes our new H max. And therefore we move the key to the node 4. I'm putting aside the hash collisions, which are of course possible, but they are typically handled kind of outside of the actual hashing algorithm. Like in Ignite, we will just regenerate the UID, for example, the node ID, if we detect collisions. And we calculate mappings, all the mappings when node starts and all that, and we'll regenerate ID if needed. So we assume that collisions, they do not happen on the actual rendezvous hashing algorithm level. So we have two outcomes, right? The first one, H4 is less than Hmax, therefore key stays on node 2. H4 larger than Hmax, therefore key moves to node 4. Which is exactly what we want, right? Because this means that any key will either stay where it currently is, or it will move to this new node that we have just added. This algorithm just out of the box ensures that none of the keys will be moved within the nodes that we currently have. And if we do the same exercise that we've had before with those all the keys that we had with 3 nodes and 4 nodes, we'll get something like this. So we'll have 2 nodes moved to the node, 2 entries, sorry, moved to the node 4, which is the new node, and there are no other data movement and no other data reshuffling between the 3 nodes that we've had prior to topology change. You can notice that basically the distribution is not that good in terms of evenness. Like with basic hashing, we had like ideal distribution with 3 nodes, like 3 entries per node, and pretty much the same distribution with 4 nodes. With rendezvous hashing, it's much worse. Like for example, when we have with 4 nodes, we have 1 entry on node 3 and 4 entries on node 1. So this is kind of a typical trade-off for distributed systems, and we have those everywhere. This kind of a reality of distributed systems, because we always have to deal with the trade-off between the price we pay for coordination between the nodes and just for distributing the data and for getting the scalability from running multiple computers, and the actual value that this distribution provides. And this is one of the typical examples, because essentially this kind of requirement of even distribution can conflict with the requirement of this what we call minimal disruption, or absence of this data reshuffling during rebalancing. And therefore, we have a little bit less even distribution. Of course, it's, on a larger data set, it's less prominent, right? You will just have several % difference between the nodes, but it might still be an issue sometimes, and it's typically fixed by using better hashing functions and whatnot and these kind of things. So let's code that. So this will be actually pretty simple. In terms of coding, it's going to be surprisingly the easiest part, because as I said, we don't really change anything on the architectural level. All we change is our hashing function, hashing algorithm. And essentially what it means in terms of our components and whatnot, it means that we need to go to the mapper and update this node method that picks partition, node for the partition number. So let's implement the algorithm. What will happen is, so we already have the topology that we got from the discovery. I will iterate through nodes, but I will also need to memorize the maximum hash value, because that's how the algorithm works. So I'll start with mean value. And also I will memorize the corresponding node, which I will just then return from as a result. So it's initially null. So all I need to do is I need to iterate through topology. So I will call it something like max hash node. All right, so for every node having the partition number, I need to calculate the hash. And I will use the one of the Guava mechanism. We need a good hashing function for this. So I will have this murmur3, for example, and I think I need to do new hasher, and I will put integer, which is the partition number first, and then I will do put long for the node ID get most significant bits, and the same for the least significant bits. So this will just calculate hash again based on the node ID and the partition number. And calculate the hash based on that and return the long value. All right. We also need to apply the ABS to get rid of negative values. And finally, if this hash that we've just calculated for this particular node is larger than maximum hash, then we update the maximum hash. And we memorize the max hash node with the current node. So, very just typical algorithm of choosing the maximum value, and we return this max hash node as a result. So that's actually it. Let's actually take a look at what we've had before. So again, like when I ran this test previously, we had 2 nodes, and then I added new node. And this new node got keys 0, 4, and 7. And let's actually see what happened on the other nodes. So we actually had 0 and 4 here on node 1. These are the 2 keys that had been moved from this node 1 to the new node, the node number 3. Our other keys that we had here is 2, 6, and 8. But if we look at the new set of keys that we had on the first node, it's not 2, 6, and 8. It's actually completely different. We also have like key number 6 was actually moved to node number 2, and we also got 1 and 5 here on the first node. So we have this data reshuffling that I've been describing before, and that we actually want to avoid. So now let's just rerun the exact same test, but with the rendezvous hashing algorithm instead of just basic hashing. All right, this is the first node. The second node, now we want to run the client with the updates, of course. So we have all the results. Everything is good so far. We got 5 keys here, 5 keys here. We will now kill the client, add one more node, and we'll then rerun without updates. All right. All right, so results are correct. So this new node got 1, 5, 6, and 7. Let's see what happened here. So for example, we do have, we used to have 5 keys, 2, 4, 5, 6, and 9. And we see actually that we have 2, 4, 9 that remained on this node, and 5, 6 has been moved to the new node, right? So that's already looks much better. So we also expect that 1 and 7 has been moved from here, and that is exactly the case. So we have 1 and 7 moved to the new node, and 0, 3, and 8 remained here. So there was no movement between the first node and the second node, which is exactly what rendezvous hashing provides. All right. So that's actually all I have. So with that, we've built a very primitive, obviously non-production ready or anything database, but it's actually functional, and it demonstrates all the basic, not all the basic, but some of the basic concepts that we have in distributed systems. So we've built just a very simple in-memory data storage with the key value API. And we also learn how we can scale it out by adding more nodes, and how we can achieve automatic request routing as well as automatic data distribution based on those multiple nodes that we have in the cluster. So with that, I also had an announcement before we go into the questions and raffle and everything else. So just a quick announcement. On May 25 this year, we have our the very first Ignite Summit, and we are of course very excited about it. It's going to be a virtual event, so everyone is welcome. Just go to ignite-summit.org and register there, and we definitely will be happy to see you there. We're going to have some really interesting speakers, different topics. We'll have speakers talking about kind of architectural stuff like today, or some just user stories about how Ignite is used, and some interesting use cases. I will also most likely talk about more of kind of future plans that we have in the project. There is some exciting stuff there as well. So you're definitely welcome. And if you have something to share, the call for papers is also open. So feel free to join us in that capacity as well. So with that, I think we can do the raffle. And then, I will answer any final questions if there are any, and then we'll wrap it up. So Francesca, do you want to take it over with the raffle?
Okay, so for our first raffle winner, we have Ayla Sambal. Our second winner is going to be Gopal Chandran, and our third winner is Tom Cooper. So congratulations to all our winners. I will be emailing you individually, and thank you for joining the meetup today.
Thank you very much, Francesca, for the raffle, and congratulations to those of you who have won the raffle prizes. If folks, if you still have some questions, this is the time to ask those questions. So you can unmute your microphones and ask the questions. We still have a few more minutes. I see that. Are there some questions in the chat?
Yeah, I'm looking at this right now. I think there is one question that we haven't addressed yet. Could you renumber your nodes to maximize reuse of partitions once you don't have to move? That's actually one of the ways. As a matter of fact, in Ignite, we used to have, along with the rendezvous affinity function, we used to have what was called, I think, fair affinity function or something like that, which I think implemented something what you're trying to imply here. It is kind of just manual. It's an algorithm of just manual choosing. Not sure how to say it. It basically just manually chose the nodes where to store certain partitions. So it was not relying on any particular hashing like this of the node IDs, but rather just manually deciding on which nodes which partition are stored. And that algorithm can actually provide better distribution with still satisfying the minimal disruption algorithm, but it has certain implications, and it introduces certain limitations in terms of how you can use the database. And especially when we go into like data collocation topics, when we want to group the data together, it actually gets complicated because the fair affinity algorithm is basically stateful. Like rendezvous function doesn't depend on any previous events that happened in the system, but fair affinity kind of created distribution based on previous distribution. So for example, in Ignite, we had a scenario when you had multiple caches that were created dynamically on different topologies. And then therefore they kind of created they had different starting points in terms of this fair affinity distribution. And then there was kind of discrepancy between how different caches were distributed. And since Ignite supports kind of all the cross-cache transactions and cross-cache SQL, that created whole sort of issues, obviously, because, distribution was not as we expected. So it is possible to a certain extent to have kind of different algorithms that just use external information to provide better distribution by still satisfying this minimal disruption requirement. But it does provide certain limitations, and we, for example, had to, get rid of it, at least for now. Maybe we'll get back to it when we figure it out. But so yeah, I don't think there are any questions in the chat. So yeah, if anyone else has any questions, just unmute yourself. And
so how often in practice do you have to repartition? In which case, I assume you need downtime to do that because there might be a lot of data movement, right? But I imagine over time, your distributions will get worse and worse if nodes are actually coming and going very much. But how much of an issue is that in practice?
Well, that's not really the case. So if you add or remove nodes, it just changes. So like if you have, so it doesn't depend, again, like rendezvous hashing, as I said, it's a stateless algorithm. So it only depends on the current topology. That's all.
Right, but you mentioned that rendezvous doesn't, for example, guarantee leveling, so it doesn't maintain that balance. So over time, might it get skewed enough that you would be motivated to repartition kind of from scratch?
I mean, yeah, it is possible theoretically, I guess, that you can get into into a certain topology which gives you a really bad distribution for some reason, but that doesn't really happen. And again, it depends only on the current topology. It doesn't depend on how many times you've changed the topology beforehand, for example. Just because of the way the algorithm is designed and implemented. So this kind of discrepancy between the amount of data stored on different nodes usually remains, more or less the same. The only thing that might create issues is that when you have, let's say you have 10 partitions, right? Like in my example. And obviously, if you have, if you add more nodes, then you can kind of run out of partitions, right? In the worst case, you will have more than 10 partitions, and therefore some of the nodes will not have any data because there's nothing to distribute. There are only 10 partitions, and the number of partitions is constant. It's really hard to change that number. To change the number of partitions, you essentially need to kind of reload all the data and all the stuff. So that's a very heavy exercise with downtimes and all that. But for that, we just, in Ignite, for example, it is 1024 partitions by default. So I've been using 10 again for simplicity, but in real system, you have much more partitions. And if you have 1024, you need much more nodes to actually go get into the situation. And if you expect larger clusters, you can increase number of partitions up front, right? If you think that you can have thousands of nodes in the cluster, and we do have users who do that, but they will just kind of expect it up front, and they will configure much more partitions initially than what we have by default. So that's kind of the only actual scenario that you can that you can find yourself in. But yeah.
Very good, thanks.
Yeah. Are there any more questions? Okay. If there are not any more questions, I would like to thank Valentin for the wonderful presentation, and also your organization for the wonderful raffle prizes that you've just given out. And obviously we have the recording, but I'm sure the participants will be also happy to have a way of getting to the source code, because definitely I would like to play around with this implementation. So maybe you can when you get a chance, you can provide that to us, and maybe the slides as well that we can share on our forum. If there are no any other questions, I would like once again, Valentin, thank you very much, and that was a wonderful presentation. Thank you. And thanks everybody for joining the workshop this evening. I'll send out some announcements of the upcoming meetups. So just look out look out for the announcement in your emails. Once again, thanks everybody, and have a good night.
Yeah, thank you everyone for coming.
Okay,
I'll share the deck, I'll share the recording and everything else.
All right, thanks. Thank you.
Thank you so much.
Bye-bye.